Hello and welcome back. Let's continue with our class of Eurocode7. We are on this chapter number 3, ground investigation and testing. And I think we have done all these points from number 1 to number 7. And from this video, we will start with this point number 8, which is about work example. So this part is kind of very important. So I will try to make maybe several videos on this part examples. Okay, so it will be about how to obtain characteristic value from field test or lab test. Okay, for this precise video we will try example with lab test. Okay, how to obtain characteristic value with lab test. So before starting the example itself, I will go to do introduction. Just to remind you few informations we did before we proceed. Okay, the first thing I would like to remind you is the definition of characteristic value itself. What is characteristic value? Okay, we have seen this in the first parts of this chapter, the early beginning of this chapter. We have defined what is derived value, and we have defined what is characteristic value. And this figure is illustration of what is this figure. From this figure we can illustrate what is derived value or what is characteristic value. Okay, so derived value are value that are obtained directly from test. Okay, test result and derived value. For example, if you do F is for field test, you will obtain the value you will obtain from that field test is a derived value. Okay, by using just some correlation. And L is lab for laboratory test, lab test 1, lab test 2. Anyway, the value you obtain from directly from tests are derived value. Okay, and then you obtain characteristic value, as you can see, geotechnical model and characteristic value of geotechnical property. So this is what we are looking for now. And these characteristic value are obtained by selection, using some selection, cautious selection, and some information related to a project and site. Okay, so in this video, the objective is to obtain how to obtain characteristic value from lab test. Okay, this is what we are going to do. So previously, I think the last video before this one, we did the video before this one. Just check the previous video. We have talked about how to estimate characteristic value. Okay, the formula to estimate characteristic value from lab test by using statistics. So this is a reminder about that. Okay, so I want to remind you also these two formula. So last video, just previous video before this video, we have talked about these two formula, how to obtain characteristic value from using statistic. Okay, so xk is characteristic value, xm is the mean, the arithmetic mean value. For example, if you have many soil samples, and each sample will give you a value, and after obtaining the value for example, if you are looking for internal friction angle or for cohesion, any geotechnical parameter, you make the average, the mean of all the value, and you will get this xm. Okay, kn is a statistical coefficient that will depend on the number of tests. We will talk about this one also, how to determine this. The value of kn are available in many probability manuals. Okay, many statistic manuals. And Vx is just the coefficient of variation. This is also a statistic, the definition. This is really related to statistics. So anyway, we are going to explain all this, but I just want to remind you that we have talked about this formula before in the previous video. And this formula as well, proposed by this reference, we have talked about this formula also before. And here, this SCU is the standard deviation. CU, undrained shear strength, maybe. Okay, so just remember these two formula. We are going to use them in this example, and maybe, hopefully, you will be able to understand them deeply. Okay, let's go. Now we start the core of this video. Okay, the main topic of this video. Worked example, characteristic value. Okay, application of statistical method to determine characteristic value of ground parameter. Okay, we are looking for ground parameter. Okay, so the following figure, this figure is explaining application of the part 1 of Eurocode 7. You can check paragraph 10 and note. So this figure, as you can see, is showing 3 borings. 1, 2, 3. Okay. So, for example, soil sample are taken from each of them, each of these 3 bodies. Okay, and 11 sample. This one, on this one we have 1, 2, 3, 4 samples taken from this bone. Okay, this one we have 1, 2, 3 samples taken from this bone, and here 1, 2, 3, 4 samples, soil samples taken from this body. Okay, so in total 11 samples are taken, and this is clay. The soil is clay, stiff clay. So what we want is to determine the undrained shear strength. Okay, undrained cohesion, the shear strength. So for that, the soil sample were tested in lab to determine the strength of the ground. Okay, the undrained shear strength. As you can see, we have several values. CU, undrained shear strength. So we can see that by looking at this value, this result of the shear strength, we can see that there is no trend. Cannot see that the shear strength is increasing with depth. For example, you cannot say that because you can see, for example, this one is higher than this one, while it is this one is smaller. There is no logic, okay, and no apparent difference between the boreholes. Like, for example, this one, the value of this one are not much different with the value obtained from this boring, as well as this one also. There is no apparent difference between. It means from horizontally there is no big difference, and vertically also there is no big difference. Okay, because of that, we can say that the undrained shear strength is normally distributed. Okay, so in statistics, maybe you know what is normal distribution. So we will consider that this is normal distribution statistically. Okay, so in this Eurocode, this example of Eurocode, there are two parts. The first part is referring to a situation where a cut is planned. Cutting, okay? You see this blue line? For example, this will be embankment, for example. You cut here, the blue line, following the blue line. It means excavation. This part will go. Then you will have a slope, okay? For making railway, for example. For making railway. So anyway, after cutting, you need, of course, to design the stability of this slope, this blue line, okay? So the geotechnical engineer has to verify the stability of the slope. And the first step in that for doing the checking the stability of the slope will be to select the characteristic value. So just for information, these are maybe the derived value. Okay, you can see there are a lot of derived value from 11 lab tests. So as geotechnical engineer, you have to select a characteristic value. You have to determine the characteristic value from these several lab tests. 11 lab tests. Okay. Then for this first example, the first part, you have to then to try to estimate a potential slip surface. And as this red line showing, the potential slip surface is this one. Okay. After identification of this potential slip surface, you can see that this slip surface is passing through, several test results. Okay. Almost all of them. Several test results. Okay. So the potential slip surface lies in the volume of the ground of which several test results have been performed. Okay. Almost all of them. So because of that, the characteristic value that you will determine, the characteristic value can be determined as cautious estimate of mean value with confidence of 95%. That means that you can say with confidence, 95% confidence, that the characteristic value can be obtained from the average, the mean value of this test, because it is a normal distribution. Okay, normal distribution, and the slip surface where the failure will happen is covering a lot of test part. Okay, all this from top to the bottom, widely it covering several test results. Do you understand? So it means you can base on the mean value, the average value of all this, say you average value of the system. Okay, so this is what I'm talking about. If you take this statistic, this graph, for example, which is illustration of graphic for interpretation of characteristic value, normal distribution. This is a normal distribution. As you can see, you have average. Okay, The average is here, the mean of the sample, the mean average. Okay, xm, this value is the mean, the average of the frequency, relative frequency of this average value is the high value. Okay, if you calculate frequency, I think this is even high school student know this. And on the contrary, the extreme value, as you can see, extreme, low extreme value, and here is upper extreme value. Okay, this is in our case, in this case of this slip surface, you will use this average value. So the frequency of this is high. Okay, frequency of this average value is high. So you will use this, and you can be sure at 95% that this average value is okay. It's okay to use average value. Okay, with 95% confidence. Okay. Next, the second part of the note in the Eurocode, this is taken from Eurocode. The second part is referring to a situation where you have a footing. This footing, this one, this is a footing. Okay. The footing is designed, and the designer, the geotechnical engineer, has to verify the ground bearing capacity. What is the bearing capacity of the soil here? Okay. Then, as you can see, in this case, this footing is, the location of this footing is, it has only, the footing has only small zone. Okay. It's not covering all the surface. It's just this very localized place, small zone of the ground. Okay, that is covering the behavior of at the limit state. For that case, this zone might be an area where the local strength might be lower. Okay, local strength might be lower than the average. So in this case, the characteristic value is a local low value. Okay, defined as 5% fractile. Okay, the meaning of this means that in this situation, you will not take the mean value. It will be, for example, this one, the extreme value, because this is just local value, local small zone area. It doesn't represent the whole area. You will not use average here. Just use this extreme. The probability, the frequency of this value is lower than the frequency. You can see relative frequency. This graph is showing relative frequency, and the x-axis is a soil parameter. Soil parameter, y-axis is relative frequency. So relative frequency of the soil, the parameter here is very low. We can say extreme, this extreme here or here. It should be maybe here. Okay. Low extreme value. Anyway, it's extreme value. Okay. So please don't be confused. Don't be consider this as the percentage of confidentiality, or how to say this. Previously, we say that 95% with confidentiality, it is okay. This is not about being confident or something. This is about the frequency. As you can see, 5% factor is here. 5%. It means just extreme value or mean value. Mean value and extreme value. Okay. So when the this 5% of factile, it means here maybe the extreme mean, the extreme low extreme value. This is 5%. So in case of the footing, this is what you are going to take. So after that, after defining everything you need, you can now go and estimate the characteristic value. Okay. So I will bring back this formula on how to estimate the characteristic value. Do you remember in the introduction of this video, I talked about this formula and this one as well. Okay. Two formulas to determine this. Okay. So the evaluation, we have 11 tests. 11 tests. Okay. So this formula is what we need to apply this formula. We need the average, the mean value. Okay. So if you addition all the 11 value here in total and you divide by 11, you will have the mean value, which will be 79 kPa. So it means the average undershare strength CU is CUM. M means mean is 79 kPa. This here is X. This is XM. Okay. Vx is just coefficient of variation. Statistic, I think even high school students know this coefficient of variation. Okay, I show you formula here. What is standard deviation? Standard deviation here, for example, please don't mind the symbols S here and sigma here. It's same, okay? This also is standard deviation in this formula. So standard deviation, the formula for standard deviation, statistic standard deviation is this one. Okay, sigma xi is like every single value, like each of them is xi, each of them, okay? Mu, this one is the mean value actually, the mean here, 79. And n is the total number of sample. So if we have to calculate the standard deviation value of this test, n will be 11. And mu will be here, the sigma, this one, 79. So what you have to do is take each of these value, for example, 76 minus 79, because the average, the mean value is 79. 76 minus 79 and square plus, because you see the sigma here, okay? Plus you go to the next value, 93 minus 79, and you put the square. You do everything for all the value, additioning everything, and divide it with the total 11 sample. And of course, you use the square root after that. Then you will obtain the standard deviation value. Okay. And if you obtain the standard deviation value, divide the standard deviation value by the mean value. Okay. And you will obtain this coefficient of variation. I hope you understand. It is 0.08. If you multiply by 100, it will be 8%. But if you don't multiply by 100, it will be 0.08. And this is what we need. In this case, it will, our coefficient of variation is, normally you should know how to calculate this. Okay. Statistic. This is really high school level statistic, I think. Anyway, so here is the value. So what we need now to calculate this characteristic value is just the Kn. The Kn is can be obtained from a lot of statistic tables. Okay, so in this we will give you the value of Kn for the two situations, this formula and this formula. You can obtain the global characteristic value. The global characteristic value is the value for the slope stability. You remember this, for the slope stability, we said we will take the average value. Okay, do you remember that? For the slope stability, it will be the average value. However, for the footing, this one, we said we will take the extreme value. The extreme value, which is 5% of fractile. Okay, so for this global characteristic value, means for the mean value, we will take the two formula. So see the average, this formula is exactly this one. Okay, don't be confused by the symbols. XK here X is CU. If you are calculating, you want to calculate undrained shaft strength, then the X, your X will be CU. If you want to calculate the unit weight, for example, then your X will be gamma. Okay, that is the meaning. So the average one, using average for the slip surface, slope stability. So this one, the X, K multiply is XM, and here CUM, this value 79, you multiply by 1 minus Kn. The Kn here, you have it here 0.55. In this case 0.55. okay, for the Kn, multiplied by the V. Vx, x here, you replace x by Cu because we are calculating Cu. Okay, so if you are calculating Cu, replace everywhere that x is, replace it by Cu. Okay, Cu, K, Cu, M, okay, Cu, V, Cu. So VCU here is here. So replace it by this value. Okay, then you will obtain this 75.5 as characteristic value for the slope stability case. Then in case of using the second formula, still for the slope stability, okay, that is very simple. The standard deviation, I explained you what is standard deviation and how to calculate it. So please calculate by yourself, okay? The average value means this one, 79 multiplied by 79 minus 0.5 times the standard deviation, this standard deviation formula. Okay. Then you will obtain 75.8. Okay. And this, we can see that in this case, the formula, this formula from this reference is giving almost same result as the statistical formula, the statistic formula. Okay. In case of the footing now, this case, then applying this formula, statistical formula. So this one in this case is the extreme low value, 5% factile. So what will be different is just the Kn. As you can see, Kn here is 1.89. So you apply the formula. This the average, the means, and range strength, which is 79. 1 minus Kn. Kn is 1.89 here. And multiply by VCU. VCU is 0.08. Okay, then you will obtain 67.2. See, as you can see, it's smaller. To be careful, just for safety, for the footing, for the foundation, this is what you are taking, 67. As you can see, this is really smaller than everything here. So after that, you have now the characteristic value of, and you can proceed. It's not finished. After characteristic value, you will need to use partial factors to obtain design value. Okay. Yeah, but that one, the partial factor, it's easy. You can find it depending on the design approach you are using. Design approach 1, 2, it depends, or 3. Okay. Okay, now the big question is, how do you determine the Kn? How do you get the value 0.55 or 1.89? How do you get this value? Because I hope that everything is clear except how these values are obtained. So this is what we are going to explain now. Okay. So application, so definition of the value of Kn, statistical parameter. So here is some formula how to obtain this. If you have the average value, do you remember this distribution, normal distribution? If you are dealing with average value and you have statistically known parameter, I will explain this known or unknown. This is the formula to obtain the Kn. T at 95% of, you are sure at confident at 95%. N is the number of samples. Okay. So in this case, average value, this formula is used to obtain Kn. Average value, in this case, statistically a unknown parameter. Okay. And this case is for the extreme value. Okay. Known parameter. Extreme value, unknown parameter. This is formula for Kn. So what is missing in this formula? What is missing is the T. The T. Okay. N is the number of sample. We know already the number of sample is 11, right? That is easy. So what is generally when we say something statistically parameter is regarded as unknown or known, we say known, the parameter is known if the coefficient of variation or a real upper limit of this factor is already known on the basis of previous data. Okay, in that case, you can say that it is known. The basis of previous data. Okay. So I think in our case here, it is not known. So about the average and extreme, this is this one. The average value is for this one. Do you remember for the slip surface, we said we should take the average value. So in that case, you should use these two formula. Average value. And this one, upper one, is where you have the known, it is known parameter. And here is a known parameter. And the definition of known parameter is here. Okay. The extreme value, these two, B1 and B2, is for extreme value. Do you remember for the footing, characteristic value of underlying system for the footing, we say that we should take the extreme value. So in that case, you should use this one or this one, depending if you are in this situation, known parameter or unknown parameter. Okay, so this is the formula how to obtain the Kn. Then is T, this T1, T. Okay, this student's T value, depending on the confidence, the level of confidence you have. In our case, we say that our level of confidence is 95%. So our level of confidence is here. We are confident at 95% that for the slip surface, the slope stability, the average value can be used. Okay, but for the footing, the extreme value, not average, the extreme low extreme value should be used. This is the meaning of this confidence, level of confidence. So in our case, our level of confidence is here. So you can calculate the value of T, this T net. When you see this infinite, this one here, it means you should focus here, because as you can see, when the value is the number n is infinite, it's constant. Okay, the value is almost constant. From here, it's constant, you can see. But if it is not, in this case, for example, n minus 1, then you take the number n minus 1. For example, n11, 11 minus 1, it is 10. Then you come on 10 and you read the value. However, this case, this one and this one, it means the value is constant already. It's same. It doesn't matter the number of the n. So that is in the case it is known parameter. Our case is here. Example, at an infinite degree of freedom, the value of T at confidence level of 95% is this value, 1.645. Okay, we have here infinite, the confidence level of 95%, and at infinite degree of freedom means around here. So the value you can read, it corresponds to about 1.60, okay, 645. Okay, this is infinite value here. Okay, here is 1.5, so here can be 1.645. This is just example. Okay, so by using this T, value of T, and using these formulas, in this case, then this graph can be plotted. See the graph, A1, A2, B1, B2. A1, let me go back and show you. This is A1, this scale. A2, this scale. B1 is this scale. B2 is this scale. Okay? Then all these graphs are plotted for the coefficient Kn. And here is number of samples. Okay? So our case is, and these two curves are for 5% fractile. Do you remember which one of for us is 5% fractile? If it in the case of the footing, the extreme value, if you want also 5% fractile or 15, but for 50% of fractile, it means mean value. Okay, that is for the case of slip surface. Do you remember? That is very important. Let me go back to explain it again. This one, the mean value is 50% of fractile. Okay, 50% of fractile is mean value. However, 5% of fractile is this one. The extreme low value is this one. So this one, 5% fractile, 50% fractile. So this is for the mean value. It means for the slip surface, slope stability one, because that one is mean, we consider the mean value of the undrained shaft. So we will use this curve. Okay, and mainly this one, the unknown one, unknown variance. Okay, you don't know the variance of the mean value. So our number of sample is number of sample is 11, right? In that case, you come here, this is 10. So it's logarithmic scale. So this is 10. It means this is 20. Okay. This is 30, 40. So it means this is 10, maybe 11 should be around here. And you plot, you go on around this curve. For the mean value, for the slope stability, okay, it will be around 0. Here is 0.5. So a little bit above 0.5. So it is 0.55. That's why you have here this 0.55 Kn for the global characteristic. Global means mean value for the slope stability. That is why you have here 0.55. I hope it is clear now. Okay. For the footing one, you remember for the footing one, it was 5% of fractile. For the footing, it was the extreme low value. So in that case, we should read here. Okay, we should read on this violet curve. Okay, and n number of sample is 11. So around here, we go up. It should be around here. If you check the y-axis, this is about 1.89, exactly what is here. So this is how these values are obtained. I think everything is clear now. Okay, but don't remember, this example is for how to obtain characteristic value using lab testing. Okay, in the next video, we will talk about how to obtain characteristic value using CPT, for example, CPT test. Okay, so that will be all for this video. Thank you very much for your time and see you next time. Okay, bye.